Thanks for inviting me today. I think it's very important for industry to share our ideas with universities and vice versa. This is a very challenging problem, sharing the spectrum between, or coexisting between radar and communication systems. And I'd like to tell you a little bit about the problems that are in this area, the need, the motivation for sharing of spectrum and coexistence. A little bit of discussion about the description of the two systems, the challenges that arise because they are sharing spectrum, and a way to measure the coexistence of the two systems. And then talk about unilateral solutions for sharing as well as cooperative, which is an emerging area, and conclude. So this is a really new topic. It's not done today per se. It will be done in the future, I believe. And there's been some activity. There's been some NTIA conferences, some workshops. 2011 had a very good one where you can go online and look at some of the technical presentations. There's policy, there's politics, there's a whole slew of regulatory issues that arise in this domain. So this is a really multi-dimensional problem that needs to be addressed. And it will have many different aspects of the solution, many dimensions to the solution as well. DARPA, the Advanced Research Projects Agency for the DoD, will be having a shared spectrum access for radar and communications program. It's in the competitive bid phase right now, so that's something that will be happening this year, starting this year. And the FCC is in a new proposed rule change rulemaking for the Citizens Broadband Service. That's around 3.5 gigahertz. So that last thing is part of the presidential mandate to free DoD spectrum, so what's typically reserved for military and federal use in the United States, within the continental United States, for commercial interests and other interests. So this is all part of an ongoing, emerging process that's causing this issue, which is this, I call it a spectrum crunch. We all have, well, a number of us, a majority of us, I would say, have devices that we are constantly able to access the internet. We have all kinds of broadband needs and services that we request all the time. And the problem is that the spectrum that's allocated to the cellular industry is limited. It's constrained, and it's not growing at a fast enough rate. So this is an FCC model that I have on the right here from 2011 that projects until 2014, where there is going to be this enormous, over 1,000% growth in traffic per cell site, and that leads to a deficit of 275 megahertz. And the spectrum that is being released from the DoD, freed up from DoD usage, is not happening at a fast enough rate. So I think we're all relatively familiar with this, that we need to, as engineers, as wireless engineers, develop better communication protocols. However, it's debatable whether we can develop them fast enough to keep up with the burgeoning need. So that is why there is this exchange or clearing of spectrum that's going on, where the FCC and with all the regulatory power that it has is able to do that, and that's why it's happening. So on the military side, this puts the military at a disadvantage and challenging it in terms of being able to continue to use its radars to fulfill its missions. Well, I'll talk more about how to address that later on. And I mean, that is the coexistence problem, is that there's a spectral encroachment and erosion of spectrum that's going on, and there needs to be technical advances and things like that need to happen. This is just an overview slide to show that at S-band, which is a well-used radar frequency band, from 3.1 gigahertz to 3.5 gigahertz, there's a number of radars, prominent radars that are used by the military. Within the United States, there is a well, that's the allocation within the United States. there is this LTE band 42 that coexists with it, and adjacent to this band is that new FCC Citizens broadband service that's opening up. Now, these are not co-channel bands. However, they're close enough in frequency where there could be interaction in adjacent, because we're not talking about ideal spectral filters here. These things have finite stop bands, attenuation in their stop bands, so that could be an issue because radars are very high power, and I'll be telling you more about that later. And if you go international, the same problem exists in countries abroad. You'll find operation of radio fixed broadband wireless down to 3.4 gigahertz. So again, that's right adjacent to the S-band radars that the Navy uses. In 2011, a study was done by the NTIA that shows that if we consider for instance, a CONOPS, a scenario might be that there is a Navy radar that's patrolling the edges of the continental United States. I'm not suggesting this happens often or at all, but if they wanted to, do some activity operating an S-band radar towards the interior of the country, these are the kinds of exclusion zones. These different bands represent different kinds of radar powers and things like that. But these are due to the blockage that's provided by the terrain, the fact that we have hills and mountains and things like that. Eventually, this is the size of the exclusion zones, and the challenge here is that exclusion zones are not a great solution because most of the population lives near the coast in the United States. So the people who would benefit from using that spectrum or being impacted by radars, that any time could be mobily traveling along the coast, well, that's a problem. So this just shows the geographic extent of the problem. And here is a test case, or here is a case of a radar not interacting well with a communication system. So in Puerto Rico in 2009, there was a well-documented case. In the 5 gigahertz UNII band, there is a mechanism that's called DFS, dynamic frequency selection, for detecting when a radar pulse is occurring and selecting a channel so essentially orthogonalizing in the frequency domain. And what happened was due to misconfigured equipment, this radio continued to interfere with the radar, and it created those dropout strobes, interference strobes that we can see spatially here for this particular weather radar. So this is an example of the kinds of degradations that can happen to a radar in the presence of just a Wi-Fi, an outdoor wireless LAN radio. In terms of how we can measure the impact of radar on radio and radio on radar, because it's a bidirectional coupling and degradation that can occur. Here's a slide that I'm borrowing from a DARPA presentation that you can find this presentation online. It's a part of John Chapin's Spark program that I mentioned earlier, and he was in this particular slide. He was saying this is the ideal representation of how to characterize interference that exists and how to spatially describe it. So in terms of space, time, and frequency, we can have interference zones where the degradation is reaching it's having such an impact that either the users of the radio would be unhappy with their service, the quality of service has diminished too far, or the radar performance is reached a critical level in terms of it's not able to fulfill its mission. So those would be interference zones, and those are kind of like, just small areas that are distributed throughout a geographic region in time and frequency. An exclusion zone is the kind of like broad stroke approach to fixing this problem, and that's where you say, well, if I have any suspicion of these interference zones existing, I'm going to make a simple kind of spatial, temporal, spectral filter or policy of not using in this location any of those resources, and that's kind of it's not a good solution. It's not an efficient solution. So the way that Dr. Chapin was proposing that the technologies could be developed and evaluated was how much can you shrink these exclusion zones down And that's, I think, a good metric to use in general going forward, even if it is challenging to measure. Certainly this is something that's easiest done in simulation. This graphic is a depiction of what is currently done, which is on the left, and in terms of orthogonalizing radar and comms, or radio networks, and what would be perhaps a goal in terms of spectrum sharing, the most efficient spectrum sharing that could go on between radios and radars. So currently we have to keep them separate in terms of their frequency. We can't have frequency reuse because when these systems intersect in time, frequency, and space, when one system receives the other, there's going to be some degradation. So there's sensitivity issues and desensitization that occurs. So that's how they do it. They separate it in terms of the frequency domain. What would be a much more efficient use of all of these resources, time, frequency, and space, would be to have a much tighter packing. So it's kind of a if this information could somehow be shared, if there was some way for the radio network to know where the radar was going to be at any particular time, it could fill and use that spectrum, reuse that frequency in an efficient way. And the challenge, of course, being this is not too different from what happens with DSA radio, is that it's difficult to make models of a dynamic user of spectrum. How can you predict what something else is going to do? So that's been kind of an impediment, I think, to developing these kinds of really efficient spectral reuse technologies. And I'll tell you a little bit more about that in a later slide. So that's one way to look at it, is that's the end goal, if we could get to that depiction on the right. In addition, by sharing the spectrum now, the radar has more spectrum, more bandwidth to use, and therefore its resolution improves, its signal to noise improves, therefore its detection capability improves. And the comms, of course, has greater capacity as well, because now it's using the radar's bandwidth as well, so its capacity is increased. The challenge in all of this work is that the radars, I think, are the long pole in the tent, is one way to put it. The radars need the modification. The communication systems that we develop, communication systems engineers develop, have many degrees of freedom and are highly adaptable. It's the radars that are not, because they own the spectrum. The policy is that radars are the primary user. They're the only user of the spectrum, and it was never designed to cooperate or coexist well with other kinds of users of spectrum. So being the primary user, the incumbent primary user, it's kind of a change in policy that needs to take place. There's very high power in the side lobes on transmit especially, and therefore when the radar is scanning around, you can't just worry about what's in the main beam of the radar, which can be quite narrow. You also have to worry about what's in the first side lobe, the second side lobe, depending on the range between the radar and the communication receivers. And of course, they're extremely high power. We're talking about gigawatts of power, EIRP, in the main lobe, so it's very high power. And they have a very wide dynamic range, so they're extremely sensitive. They're receiving backscatter from targets that's very, very weak, so they have very good receivers, very low noise, and any sort of interference degrades their performance. And there's the issue of sensitivity of their mission. The military radars in particular, we can't really discuss their waveforms. We can't talk too much about their performance characterizations. So co-designing radar and communication systems and coexisting them it's a challenge to do bidirectionally. As I mentioned before, very high power. One way to express it is in terms of millions of microwave ovens within the pulse. And they, especially electronically steered phased arrays, they move very quickly. And they're unpredictable in terms of where their main beam is pointing at any particular time. So it's difficult to make models. It's difficult to predict. So it's a challenging situation in terms of coexisting between radars and radios. The radar equation, you might have seen this before, this is just out of a textbook, is essentially a good way to explain why the radar uses so much power, because two reasons. It's a bidirectional path loss as opposed to a communication system where you only have to worry about the spreading of the wavefront in one direction, so you get your R² path loss. Now you have an R to the 4th path loss that occurs, and the RCS of your targets, the radar cross-section, is very, very low. We're talking about missiles and planes being on the order, looking like birds, you know, the RCS of a bird. So clearly we require higher power to illuminate such targets and very sensitive receivers in order to detect them. The characterization of the amount of interference coupling from one system into another, this is particularly important for the adjacent band aspect of radars. Radars are not, they have their own spectral characteristics in terms of the transmit noise mask is, they put energy out at other frequencies because they are non-ideal emitters. And they also receive energy at other frequencies because they have limited receive selectivity. So this is a useful way to look, and it's a convention of electromagnetic interference analysis, to look at it in terms of two different terms. One being the adjacent channel sensitivity and the other being adjacent channel leakage ratio. And from those two terms, you can calculate the interference rejection ratio. So I don't need to say too much about that. And of course, the high level key performance parameters associated with these two systems. For communication systems, it's the standard bit error rate, packet error rate, quality of service type metrics. And for the radar, we have to worry about things like probability of detection, misdetection, false alarm. And if those are held constant, which they often are when designing a system or operating a mission, then it's the operating range that will fluctuate. That's, you know, if you have a minimum constraint associated with the actual detection capabilities of the radar, then as interference is introduced, it's the range that will be degraded. So that's one way to look at it. In terms of the unilateral techniques, so these would be, the reason I use unilateral is because these are techniques that are not cooperative. There's no co-design going on. It might even just be the radar or the radio network independently taking these actions in order to maximize their coexistence. So one very simple approach is do not illuminate or receive using the radar's high degrees of freedom in terms of its ability to beamform at low elevation angles. Radars are, if you talk about ground-based radars, the communication systems are on the horizon, you know, or below the horizon relative to the radar. Well, if it doesn't illuminate or transmit, if it doesn't transmit or receive at those angles, then it's essentially spatially notched that interference, and it's not affected. Another more physical way to do it is actually around a radar site, if it's a fixed site, a ground-based radar, is to introduce fencing, physical fencing that acts as a blocker for the radar. A more eloquent and or sophisticated approach is to actually use phase only transmit nulling. So in this case, by using a weighting of the phase shifters, you're able to shape the effectively null on the horizon, and that's what this particular case is showing, where you have the beam pointing off to the side there, but along the horizon, which is in UV in sign space, is that curved line there, you do not emit any power. And it's important to use phase only so that you don't diminish the power in the main lobe. So that's why it's a phase only technique. It's not an amplitude weighting on that across that array. Of course, another also more conventional plan is just to tailor the frequency response. Don't use frequencies that are known to align with communication systems in your area. Use less bandwidth on those frequencies. Or actually insert better physical filtering between, so these would be like cavity filters that further tailor the transmit waveform of the radar so that it doesn't interfere in adjacent bands. In terms of the communication system, if the array of the base station antenna has an array element associated with it, of course, it could do beamforming and nulling. So if it has those degrees of freedom, spatial degrees of freedom, that's possible. It's possible through careful planning and management of the base station to point the base station sector antennas, if they're directional, away from the radar. So that's a very fundamental, basic concept. Of course, that would require perhaps additional base stations to be located in such a way that you're covering all your subscribers, yet you are not radiating towards or receiving towards the radar. And of course, just down tilting the antennas. So these are all, relatively rudimentary, low sophistication approaches. And the last thing, of course, is some sort of dynamic channel allocation. So self-organizing networks that are part of 4G systems should be able to do some of these things. So there's some plans, or there's some research that's going on in terms of looking at the capabilities of SON in resolving some of the coexistence issues itself. Moving into the cooperative sharing of spectrum, I'd like to tell you more in depth about what this DARPA program is about. I can't tell too much about what we proposed. Fortunately, the slides that I'm about to present have quite a bit of information that are indicating or give us a good amount of ideas in terms of how if information could be shared. This is the basis of this program. If information could be shared between radars and radios in terms of where the radar was, which frequencies it was using, any information that could be shared between the radar and the radio network, what could be done in order to improve the coexistence? So that and this is in contrast to the kinds of technologies that I was just describing, or something like cognitive radio, which is a unilateral solution. That is a radio or a radio network that is sensing its environment and reacting to it. What we're proposing here is a system that the radar and the radio communicate and actually exchange information and make better decisions as a result and react more intelligently. This slide shows over time that as time goes on, the radar, the amount of spectrum that it has is being reduced. So on the x-axis you have from 1980 to 2020. On the y-axis is the integration of the total amount of spectrum from 400 megahertz to 6 gigahertz. How much is allocated per service? So we're comparing radar to communications, to other services, other RF services. And in 1980, there was, from 1980 to 2012, there's been a reduction in the amount of radar allocation, and there's been this explosion in cellular. So there's several hundred megahertz being allocated and dedicated to cellular operation. As time goes on into 2020, the predicted amount is that radar will be further reduced, as we know it's intended to be reduced, and the amount of cellular allocation will grow. The issue with this is that it's not going to grow enough in order to meet the 1,000 time increase in spectrum that is required, or the 1,000 increase in the amount of data that will be transmitted at that time. So the proposal is that by sharing spectrum, you can actually now, as a function of dynamically where you are in the world and what is going on in that part of the world, that spectrum now is a shared resource. It's not statically allocated to either the radar or the radio, and depending on what's going on, either service can use it dynamically. So that's where more spectrum is available. It's kind of like, just the most intelligent, most efficient reuse of spectrum that could be envisioned. That's the plan. That's what this program is about. That's the goal of it. So both services improve. This is a nice way to show the taxonomy of different kinds of approaches to solving this problem. Going across the top, we have different degrees of information sharing between the two systems. Uncoupled, where no information is shared, that's what we currently do today. Loosely coupled, where there is sharing of information, and tightly coupled, where it's envisioned that the radar and radio could actually control each other to some degree under the right circumstances. And across the y-axis here, we have the different techniques and the different uses of that information. So there's the isolation, which is harkening back to exclusion zones. There's the actual sharing of the spectrum, which is done when there's the right kind of information is exchanged. And there's synergies where, again, the radar, it goes beyond spectrum sharing. Now we're actually talking about sharing of hardware. So this is sharing of a different kind of resources, a different level of resource sharing. So there are some examples that are given here that was labeled by Dr. Chapin, showing DSA radio as working in the loosely coupled area to the uncoupled area for isolation. I would also say that dynamic TV whitespace databases live in the, I think you could claim they live in the uncoupled isolation block there. They're static assignments of what frequencies are available as a function of geographic location. Under the sharing, there have been these device separation techniques, which are nulling and notching spatial spectral separation between the two systems, and that have existed when there was no information sharing. So what is new about this program, and what is interesting about this research, and I think it's the future of how radars and radios will share spectrum, is what is going on in the red box and the blue box. In the red box, we have a fast sharing of information between the radar and the radio network. So what could be done with that information? Well, it depends what it is. If it's the radar schedule, for instance, into the future, well, then the radio network can make a complementary plan in terms of when it's going to transmit, so that they're not overlapping in time and frequency. And if you remember the slide that I showed, the figure that I showed several slides ago, that showed the tight packing in time, frequency, and space of radio communications around radar transmissions, radar pulses, and then the reception of the backscatter, well, that would be one way to achieve that, perhaps. So that's an area of open research as to how that could be done. How would you share that information? How would you represent it? And then dealing with some of the operational security issues that arise from that, because now we're talking about sharing what is considered sensitive information, and then that would have to be mitigated so that it could be done. to say that. So that's an example of a fast. That's leveraging shared information, sharing the spectrum, reusing the spectrum in a very tightly coordinated way. Another level of spectrum sharing is synergy, is a synergistic operation, and that is where the radio and the radar are actually able to help each other. You should ask yourself, under what circumstance would this be a reasonable assumption? You know, why would a radar and a radio help each other? If it's military radar and military radio, okay, that makes sense. You know, they both have the same customer. If it's a commercial radio and a military radar, it might be a little more difficult to imagine, but it is possible that there could be win-win scenarios where, under the right circumstances, the commercial network, the radar could perhaps provide a relay function to the commercial network, and then under a different circumstance where there's a higher priority associated with the radar, the commercial network could emit some waveform that the radar could receive, for instance. I'm just suggesting hypothetical techniques, but it's that kind of exchange and sharing of spectrum and sharing of information, and possibly control, where one controls the other, that is envisioned one day with a new radar system. So that's not possible today, but in the future it could be possible. So a little more information about some of the uses and techniques that could be used if you could share information. The geographic isolation, if it would be possible for the radar to publish its location into a dynamic database, for instance. Now, this is like an extension, a growth of what's going on with the TV whitespace database, which is a static database. If those radars could publish their location, radios that are in certain geographic areas would know whether there is a radar using those frequencies or not, and adapt their behavior, reuse those frequencies if they were available. That's an example again where now the radar is publishing into this. If it's a commercial network, it would be a publicly available database of radar locations. Well, that does open up some operational security concerns, so that would have to be addressed. Another technique is, as I mentioned before, beam schedule, which is where the radar is sharing its schedule into the advance, into the future, and a radio is making an appropriate decision to either transmit or non-transmit or move to a different frequency. So that's another fast and tightly coupled. The first case, the DSA database, is, I'd say, a slow time adaptation, whereas the beam avoidance is a fast time. In terms of the path loss estimation, it's an interesting idea that radars possess a high degree of freedom in terms of their spatial, their aperture. They have many elements. They're able to form beams. They're able to form nulls, and they're able to do a lot of spatial filtering. Radio networks don't have this capability. They have few antennas. They have, a couple at most today. But what they do have is geodiversity in terms of they are in a geographic region with respect to the radar. They're distributed in many different locations. They can be behind buildings, inside buildings, in a variety of RF shadowed environments. If the radios that were in those shadows knew that they were in a shadow with respect to the radar, they can transmit at a higher power. And they could perhaps transmit and be received by a radio that's not in the shadow, that's exposed, it's an exposed node to the radar, and achieve a high enough SNR at that exposed node so that the message could be received successfully. So that's an example of if you could have that knowledge, if that knowledge was available via some sort of protocol, some sort of channel sounding with respect to the radar, to the interference channel, you could exploit that knowledge. So that's the idea behind this particular. It's kind of like I guess you could say a mechanism. And finally, interference. The reactive interference mitigation is a technique related to what happened in Puerto Rico in terms of that example that I gave at the beginning of the presentation, where if the devices are misconfigured, if they're malfunctioning, and there's hundreds of thousands or millions of devices, this could be very disruptive to the radar's operation and vice versa. So it's important for there to be strong and fast mechanisms to stop malfunctioning devices. So I think this is a really good point, and would definitely be part of any program that was suggesting that if you wanted to share spectrum, you have to be very cautious of those kinds of issues. The last aspect of this program is what could be done in terms of, so those were systems level separation techniques, and those require sharing of information and then exploitation of degrees of freedom that are protocol centric. I'd like to think of those as like MAC layer type dynamic resource allocation techniques. This is more of a electromagnetic or physical layer allocation of resources that is also can be very powerful, and this could also benefit from sharing of information. If a radio node could be providing a feedback channel to a radar so that interference levels that are measured as the radar transmits interference, there could be measurement intervals where the radio characterizes the amount of interference as measured at the radio. It could improve its nulling, essentially, because otherwise it's an open loop nulling that it's attempting to do. So this is an example of how information sharing could improve the operation of these device level separation techniques, and these could be done in the time and frequency domain as well. So in conclusion, I think I've made a strong case that radars and radios do need to share spectrum, do need to coexist in the future, in the near term, and going far into the future, because of all of the burgeoning need for spectrum. It is possible today to use mature device separation techniques. That is the lowest hanging fruit, I think. The system separation techniques don't exist because radars and radios don't share information at this time. That would be developed under future work. There are lots of degrees of freedom, enormous degrees of freedom in terms of the radar's ability. It's good to keep this in mind when you're designing protocols and techniques. There are many degrees of freedom present in the aperture and in the signal processing of the radar, and that's not necessarily the case in a radio network, where it's one of its degrees of freedom that I hadn't really considered before is in terms of its geodiversity. Sure, there can be radios that have multiple antennas, but it doesn't scale very high. Where they have some degrees of freedom is in terms of the way that their relationship is back to the radar, in terms of the shadowing, the independent shadowing that each radio has. And if the information could be shared explicitly, this really opens up new paradigms in terms of how spectrum can be shared, because these new mechanisms become available, which are just not possible today with unilateral coexistence techniques. And this is being developed. I mean, there are the FCC regulations are being changed as we speak, and there is investment going on by the DoD. Here are some references. I mentioned the DARPA program, the FCC's change in their rulemaking. A couple years ago, I had a paper that talked about some of the more traditional techniques that I described there, device separation techniques. And that's it.